But they didn't have the intuition to observe rainfall, and it is indeed very easy. So it cannot be the motivation that they didn't have the tools. It's very easy to measure rainfall, but probably they didn't need it, and because probably they didn't suffer from lack of water as we are suffering today. Indeed, there were ancient populations that suffered a little bit from lack of water, and they made some measurement, but this measurement was not systematic. If you think to the ancient Egyptians, they made measurements of the water level in the Nile, and in some countries also they measured rainfall, but was not systematic. Because keep in mind that they didn't relate directly, they didn't know, and this may seem strange to you, but it's not. They didn't know that river flow was directly connected to rainfall. They didn't know that. And this intuition came recently in about around 1500, 1600. And you know, the reason for that, because it may seem to you completely unreasonable that humans didn't understand that river flow was fed by rainfall. But actually, river flow sometimes is fed by snowmelt and from groundwater resources. And sometimes rivers are very long, especially the ancient rivers from which people took water, they are very long. So sometimes they had plenty of water without any rainfall, and sometimes they didn't have any water even when it was raining. And communication was not like today, very quick. They didn't know, for instance, in the lower part of the Po River, they suddenly got flooded, in some cases, without any rainfall. They didn't know that in the Alps there was a snowmelt event, or a storm, and therefore they didn't understand that, and they assumed that the river flow was given by groundwater resources, because this is a reasonable intuition. If you see a lot of water in the river, no rain, so the intuition may be that it's something coming from somewhere underground. And so probably for this reason as well, they didn't feel the necessity to measure rainfall. So we started relatively recently, and this is something that is, and in Italy we started, something that is unfortunate, because if we look at the oldest systematic rainfall time series, it is the one that was collected in Padua. They started in 1725, so it's about 300 years now. And this is the longest rainfall series in the world, and it is collected at daily time scale. They started at daily time scale. And then in Italy, the second longest time series is again Italian, two time series, Florence and Genoa, 1813, so about 200 years. Bologna, I think they started in 1825. The series in Bologna is daily, and it's considered to be one of the most significant in the world, and is presented as a significant example in several textbooks related to meteorological analysis. As I said, this is unfortunate because several questions that today we have about climate change would be easy to answer had we available a time series of daily rainfall 2,000 years long, which in principle would be possible if people had the intuition to start measuring rainfall. But they, as I said, they didn't. And but still, let me emphasize once again, it's much easier to measure rainfall than river flow. River flow is difficult to measure. So the result is that if we look at data today, information on water resources, we have a lot of information related to rainfall. It's very dense in space. It's quite dense in time. We have several time series with daily observations. We started recently with sub-daily observations. It's much more information with respect to river flow. So it's quite obvious that sometimes we need to make design related to river flows. We don't have any data, so we look at rainfall because for rainfall we have data. I mentioned that we started recently to measure short-term rainfall, sub-daily. Indeed, this measurement started around beginning of 20th century, about 100 years ago, in Italy and in other countries, but they are not very systematic. And these observations are not very continuous, meaning that there were interruptions. And it's only in the past 20, 30 years that we started a systematic collection of intensive rainfall, intense. Keep in mind that short duration rainfall is the more intense. And this is clear. If you think about showers, where you get completely wet in 30 seconds, which means that rainfall is very intense. Typically, they occur in summer, and they last for a short time. If you think about long rainfall, 1 week, it's not very intense. It's something very extended in space, occurs typically in the fall season in Italy. It's a different mechanism, and it's not intense. Okay, so one important thing to consider is that this observation of intense rainfall are very sparse in space and time, and it's difficult to reach conclusions about intense rainfall regime. This is very relevant because, of course, today there is the concern that intense rainfall is increased, meaning that rainfall intensity is increased for extreme events and induced by climate change. Actually, if you look at the observation, there is no information, no enough information to reach any conclusion. You don't see any change if you look at the data. So people say that the reason why you don't see any change may be that the data are very sparse, are not enough. On the other hand, when you listen to people saying that the rainfall intensity is doubled, or sometimes you listen 10 times, this is completely unsupported. This is fake news. And it's easy to realize it because you just have to look for data. So when you listen to people saying rainfall intensity is doubled, and you ask for the data, and you judge from the answer if it's supported or not. Maybe that in some locations rainfall intensity is doubled. There are also local effects sometimes which can justify such a statement. But let's look for the justifications in order to recognize the fake news. Okay? So let's concentrate on rainfall runoff modeling. And what does a rainfall runoff model? And okay, let's look at this figure. This is the water cycle. It's something that we learn from the primary school or the secondary school, maybe. But we know more or less how it works, so we don't discuss about it. Evaporation, condensation, clouds, and then rainfall or snow, and then you have surface runoff and groundwater flow, and there are a lot of these phenomena that we don't understand. This is one important thing to keep in mind. The only one important thing I ask you to keep in mind about the water cycle. We don't understand it completely. So in several of these processes, there are some of them that we cannot observe, and therefore, you know, we can just have an idea, elaborate an idea. In some cases, we can understand how it works, but we cannot measure these fluxes. And this is another strong limitation. So groundwater flow, direct groundwater flow to the oceans, we cannot measure it. There are models trying to predict it, but scientists recognize their uncertainty. And as I said, some of these fluxes cannot be measured. Keep in mind that the water cycle is an extremely important component of the climate system, which is not completely acknowledged by the literature. So the fact that there are fluxes here that we cannot model, we cannot reproduce because we cannot see them, we cannot estimate them, it means that this is a considerable uncertainty, not only for hydrological models, but also for climate models. I have some interactions with climate scientists that repeatedly asked me, but is there a way to improve our knowledge of these direct fluxes of groundwater into the oceans? And you know, this is extremely difficult. Okay, so hydrological models reproduce the water cycle. And usually we focus on specific parts. The rainfall runoff model focuses on the transformation of rainfall into surface flow or surface runoff. Typically we focus on a limited portion of the water cycle in order to reduce uncertainty. Because of course, if the complexity of the whole system is very relevant, we try to focus on parts of the system that are that have less complexity. Rainfall runoff modeling is something that, you know, it's easier to understand with respect to the whole cycle. Okay, so what do we have to do in order to build a mathematical model? In order to build a mathematical model, we have clearly to identify what is the output variable that we need. In our case, it's river flow. Typically, the output variable is our design variable. For us, the river flow is water resources availability. And therefore, this is our design variable. So this is the first step. Identify the output variable, and then identify the input variable. Okay? The input variable, in this case, is rainfall. I say rainfall, I can say precipitation, probably would be better. In technical terms, we use rainfall runoff modeling. People use that. Don't use precipitation runoff modeling. But actually, when we say rainfall, we also include snow in many of the models. So, output variables, input variables, and then there is a first difficult step to identify whether we need state variables. What are state variables? A terminology that may be a bit concerning for an engineer, shouldn't be. State variables are variables that I need to describe the system, and are not design variables, but I need them to derive the design variables. I need to describe the state of the system to derive design variables. So, let me make an example, like groundwater aquifer. I said I take some water and I want to know if I can keep taking it. An essential knowledge that I need is the storage of the aquifer. And then there is another essential knowledge that is recharge of the aquifer. The recharge is the input variable. The withdrawal is my output variable. But I need the storage. What is the storage? It's describing the state of the system. Because of course, if I have a lot of storage, the aquifer can compensate for my withdrawal. If the storage is zero, I cannot withdraw more than what is replenished. So, I mean, storage is extremely important to know, but it's not an input variable, it's not an output variable, it's a state variable. So, I need to identify what are the state variables that I need. And keep in mind that even this difference between input, output, state variables, sometimes there are some variables that one cannot really distinguish if they are output variables or state variables. Don't be concerned. The only thing that you need is to identify what are the unknowns in your problem. So storage is an unknown that you need. So I can call it state variable, but the important thing is that you have to identify the unknowns. And then you need equation to describe these unknowns as a function of inputs, and we call them constitutive equations of the model. It's important to identify the unknowns because for each unknown you need an equation. I'll make some practical examples very soon from which you will understand what is the meaning of an unknown, a state variable, or an output variable. And then, as I said, I need these equations, and these equations relate the input to the output through the state variables. I need as many equations as unknowns. And what are the equations that I can use? At this stage, knowledge comes into play. Knowledge of the theory, knowledge of the engineer. So, what is the typical approach of the engineer? Understand what kind of problems I have to deal with. So in this case, is movement of water, simply. Rainfall that falls over the ground and then flows over the ground and gets together into a river. Movement of water, movement of a body, law of physics, very simply. So I am describing the movement of a fluid, law of physics, and in particular fluid mechanics. It's very simple. And therefore, law of physics, Newton laws, conservation of energy, conservation of momentum, conservation of mass. This is typically what I need. Just that. So let me try to be more clear. Conservation of mass is clear to you what it means. I measure rainfall, so I know the mass of rainfall. I impose the conservation of the mass in order to get information of how much water I find in the river. Perfect. Conservation of energy, conservation of momentum. They are very similar. And momentum is quantità di moto in Italian. It's the product of mass times velocity. Mass times velocity. And there is a fundamental difference between momentum and energy. Momentum is a vector, energy is a scalar. In very poor words, I impose conservation of energy when I'm not interested in describing the vector of the river flow, which means direction. If I'm just interested in estimating the river flow, river discharge, and not its velocity, for instance, then conservation of energy is fine. If I also want to know the direction that water takes, like when I want to model a flood, then energy is not enough because it's a scalar, doesn't describe the vector. And then momentum is the equation. And therefore, when we talk about fluid mechanics, there are two basic equations that describe fluid mechanics. Just two. Conservation of mass, conservation of momentum. In some cases, conservation of momentum reduces to conservation of energy. It's extremely simple. It's more difficult to explain than to apply. So, keep in mind this. Movement of water, physics, in particular fluid mechanics. Fluid mechanics is described by just two equations. Conservation of mass, conservation of momentum, which implies conservation of energy and reduces to conservation of energy in some cases. Extremely simple. It's simple, but still these equations can be applied in very complicated forms because this is a dynamical problem, depends on time. And it takes place in space. The movement of water takes place a long time and in space. And therefore we have four coordinates: time, x, y, z. So this equation actually are 3D equations and they are dynamical. It's extremely complicated, so we need to simplify it. In hydrology we simplify everything. It's not like fluid mechanics. Hydrology is much simpler. And therefore, we have this need of reducing the complexity. So, as I said, equations very simple, but they are 3D, three-dimensional, meaning that movement takes place in whatever direction in space, and they are dynamical, so they evolve in time. Okay, that's it. Now, let's try to understand how these equations can be applied. But before moving forward, keep in mind, and I already told you, that we can also rely on empirical equations. So it's not necessary that we start from the knowledge of physics, it's not necessary that we start from conservation of mass or momentum. We can also use empirical equations, and indeed in hydrology we use them. And this is the way people started. So, the first people starting hydraulics, hydrology, they started from observations, in some cases lab observations, and they, starting from observations, they tried to explain the observations with mathematical relationships that were empirical. Okay, let's make a couple of examples. The first one is the most important by far rainfall runoff model that we have available. It's very rough, but still it's the most important. It's called the rational formula. Can you please raise your hand if you already know about it? Nobody. Rational formula, formula razionale, nobody. Did you study basic hydrology?
The rational method.
Rational method. You know it. So rational method, how many? Just raise your hand, just to understand. Okay, okay. At least, let's say at least half of you, but maybe more than half. It's good because I'm not spending much time on it. But the rational method was conceived by an Irish engineer in, I think it was 1859, okay, 1851, and he was Irish, and then it was reproposed or formalized in a more precise way by English engineer about around, I think it was 1870, something like that. So basically they understood that there is a linear proportion. They assumed that there is a linear proportion between the river flow. Here you don't see time. I'll explain to you why you don't see time there. And the reason is, I want to anticipate it. The reason is that it was conceived for describing the peak flow of an hydrograph. You know what is an hydrograph? It refers typically to a diagram of river flow against time. Okay? And they wanted to predict the flood flow by referring to a defined location, to an assigned location. And therefore they were not interested in reproducing Q depending on T. They were interested in reproducing the peak, the max flow. And therefore, this is the reason why in the rational formula, in its classical form, you don't see the dependence on time. Okay. So they assumed that the peak flow, the river flow anyway, can be expressed as the product of the area of the contributing catchment to the river, or anyway, to the water course. It may also be an artificial channel, maybe a sewer system. Area of the contributing catchment times rainfall intensity times a reduction coefficient, which is adimensional. So, let me write it here, because in terms of units, the unit of Q should be equal to the unit of E times the unit of A, which is fine because I'm not displaying the unit of C because it's adimensional. The unit of A is L squared. And let me write it here. L squared, length squared. The unit of rainfall intensity. Rainfall is measured as a length. Is rainfall depth, which is a length, divided by time, intensity, divided by time. So this is L divided by T. The product is L cube divided by T, which is fine because it's river flow. I already defined to you what is a catchment, correct? We already introduced it. Okay? Am I right? Yes. Okay, I'm quite sure that I will introduce a catchment. So the area of the catchment is the collector. So it rains over there with a certain intensity, length over time. I multiply rainfall for the area of the catchment, I get the river flow. It's extremely simple. And reduction coefficient, why? Because not all the rainfall that touches the ground reaches the river. There are some losses, like evaporation, like deep percolation. So we know that. And therefore they have this intuition to... hai bisogno di entrare? Ok. Okay. And therefore they have this intuition to express the river flow in this way. What is the assumption? There are several assumptions here. And let me discuss a couple of them. Because there are, people identified 10 assumptions here. I don't want to discuss all of them. And there is a dominant assumption that is linearity. This is a linear equation, linearity. So, I think it is important that I recap what is the meaning of a linear equation. Okay? In technical, very poor words, the linear equation means that if you depict a graph here of what is the independent variable here is rainfall, I. What is the dependent variable here? Design variable is Q. If we depict a graph of Q against I, it's a straight line. This is linearity. It's an implication of linearity. How is linearity defined? And keep it in mind because it's extremely important. As an engineer, you have to perfectly understand what is the meaning of a linear function and what is the meaning of a nonlinear function. I didn't realize it when I was a student. I thought, oh, these are mathematical boring stuff. No, it is extremely important to understand the difference. And therefore, this is why let me dedicate a couple of minutes. There are two conditions that must be satisfied, necessary and sufficient conditions in order to define a linear equation. So if f, the linear equation is f, the two conditions are f c a is equal to c f a, where c is a constant, and f a plus b is equal to fa plus fb. So if you have a function f that is satisfying these two conditions, these are necessary and sufficient conditions to state that f is linear. Look at this second one. This is the superimposition principle. Extremely important for an engineer. A linear function, a linear process implies superimposition of the effects. Extremely important for an engineer. For a non-linear function, this doesn't occur. It's not true. So it may happen that two effects generate an outcome that is much higher than the summation of the two individual effects. And this is very important for an engineer. You may have a small earthquake and the building is fine. Another small earthquake and the building is fine. If they occur together, the building collapses. Okay? Or, in terms of hydrology, you have a small rainfall, nothing happens. You have another small rainfall after 1 month, nothing happens. You have the two small rainfall occurring one after the other, and you get a flood. This is non-linearity. Okay. So, they assumed linearity. This is, of course, not true. And I give you a very simple example. I just gave it to you. Rainfall intensity, I cannot say that the river flow that is due to the summation of two rainfall intensity is given by the summation by the two river flows due to the two individual intensities. And the explanation of this is in the proverb, it does rain on the wet. What does this proverb mean? That if you get rain on the dry, you don't care. If it rains on the wet, you care. So it means that the same rainfall produces a different effect if there was another rainfall before. Okay? So you may have QA, river flow of A, is fine. QB is fine. And QA plus B is not QA plus QB. Because QB occurs on a wet soil here. Here not necessarily. So if you have QA on dry soil, QB on dry soil, if you sum A plus B, B is occurring on wet soil. So they assume linearity. And another assumption is, very relevant, is that rainfall is uniform over the catchment, which is not the case. We know that rainfall is spatially varying. But still, we understand that this relationship is reasonable, and they could explain several data. Okay, what can we recognize here? So this is an empirical equation. It was derived empirically. But, and this is another interesting consideration, we can recognize here conservation of mass. I mean, the empirical equation, if it is correct, of course, should match the equation that you derived with deductive methods. In fact, here there is conservation of mass. And given that they recognize that mass is not fully conserved, they introduced the coefficient C. Very easy. And so, I mean, conservation of mass, you have to take it in mathematical terms. The fact that you have some loss of water, evaporation, deep percolation, doesn't imply that you cannot impose the conservation of mass. Mass is anyway conserved, and you take into account the losses. So here there is conservation of mass. And then you may tell me, but what about conservation of energy? And I'm talking about energy because I'm describing the river flow here. No direction, no velocity. Okay, so no direction, let me say. So you could say, I can see conservation of energy here, which is correct, but I think that indeed, if we make some reasoning, we can recognize even conservation of energy. And I think it is interesting that we dedicate 5 minutes to understand what I'm saying, because it gives to you an example of what is understanding. And keep in mind, I'm referring now to the rational formula, which refers to floods. And so we are not really in the center of gravity of our topic. Our topic is not floods. Our topic is water resources availability. But I think this is a very good example that it's a good way to start. Because describing water resources availability, describing droughts, is extremely more difficult with respect to describing floods, because floods are more linear, and they are more linear with respect to droughts. In fact, I'm showing an example of a linear function. And before I move forward, keep in mind that C is a constant. This is another assumption. And actually, you know, losses are not constant. You know that they vary in time, and they may vary depending on rainfall. But if you make C depending on rainfall or depending on time, then the equation is no more linear. Okay, linearity in mathematical terms is expressed by this. If you make a numerical example, try to make, if you want to understand this numerically, try to make an Excel table and make C depending on I. It's no more linear. You make the graph and you understand. It's quadratic. If C depends on I, linearly maybe, then you have a double dependence, I times I, and therefore it's quadratic. So you have to understand that a linear equation works if you take these coefficients constant. And before moving forward, let me make a consideration about C. C is a coefficient. I called it a coefficient, a reductive coefficient. It's something that cannot be measured. It's something that is introduced in order to account for processes that I cannot really measure and understand. And is something that gives flexibility to this relationship. It's still linear, this relationship, but I can change the slope. C is the slope. A is different, it's something that I can measure. So these coefficients that are introduced for the sake of providing flexibility and don't change